Hi, it's Gary, and thanks for joining me on this episode. In episode 5 and 6, I started a discussion to introduce some concepts of how weight and stiffness affect vibrating instruments like a guitar, and how those factors can influence things like the bass to treble balance, the warmth or relative brightness of a guitar. And in this episode, I'd like to give you some concrete examples of how the physical properties of wood, like you see here, can affect your selection process. And so we'll actually listen to some pieces of wood, tapping them, and then I'll explain what the physical properties are that dictate how they sound when we tap them. And I think it'll give you some ideas on how you can select wood in your own building. And I think you can use this selection process not just for starting your project, but thinking of it more as a part of the design of your guitar. And the more that you understand about the material and acoustic properties of the material, then you'll have just a better awareness of the pieces of wood that you will be carrying forward. So let's move over to the workbench now and get into this. Today we're going to be talking about the selection of soundboards and how their material properties feed into their acoustic properties, and I hope that this will give you a foundation which you can apply to your own building style. Maybe you're not going to apply these specific techniques, but I hope this basic information will help you a lot. So when I select soundboards, the best scenario for me is to go to a tone wood producer where I can select from maybe thousands of sets like you see in this palette. Now that can be kind of daunting and a lot of work, but it can also be exhilarating because to think that I have at my disposal thousands of sets from which I can choose and bring home the best sets to my workshop where I can further scrutinize. So I'm just trying to get a ballpark of really reasonable soundboard choices back to the workshop. Okay, so one of the first things that I'm going to do is to check for the vertical grain, which we talked about in episode 4, which is produced by radial cutting. So by vertical grain, or also known as quarter sawing, I want perfectly vertical grain which is perpendicular to the face of the soundboard. And you can select pretty quickly based on that. And then next I want to know something just generally about the acoustic properties, so I will tap. And you probably always wondered, what are these luthiers doing tapping their tone wood? So in today's video I have a high quality mic feeding into my laptop, which is running a recording software, so we can hear some high quality sounds coming from these. But what I'm looking for is vibrancy and ease which the sound comes out of the board, and I'm not looking for a particular pitch, and we'll talk about the relationship of the material properties to the pitch later in more detail, but I'm looking for sustain and just a general sense that this is going to be a highly resonant piece of wood. All right, after that I want to know something about the stiffness, which you can flex, and it's kind of difficult to get a good read when these pieces of tone wood are maybe 2 to 3 times the thickness of the eventual soundboard in your guitar. But nonetheless, I'm going to show you how density is highly related to the stiffness in this direction, which is important because that is the direction which resists the tension of the strings. All right, so we'll talk about density and stiffness and its relationship to pitch in depth in a moment. But after that, then you might notice that I haven't talked about the cosmetic look, the number of grains per inch, the straightness of the grain across the board. And I, as well as many luthiers, might probably agree that that is much lower on the list, although in forums you might hear that that's really important. But we know that we've all played some really great guitars by celebrated luthiers where we've seen very ugly grain, and so we know right off the bat that that can't be the deciding factor. And in my experience, that has not been a deciding factor. The other material properties and the acoustic properties far outweigh the actual cosmetic look. All right, so now that we've gotten that out of the way, we can get into the specifics of the material properties and the acoustic properties. You probably don't have 1,000 sets to choose from, but even if you bought a couple of sets online and you have them in your workshop and you're trying to decide what to build with, these type of comparisons can be very meaningful, especially down the line after you build your guitar and you want to refer back to the physical data to try to make some sense out of what you're hearing. So let's get into this now, and what I have is a stack of book match halves of cedar and spruce, and everything I cut to exactly the same length, width, and thickness so that we can directly compare. And what we will hear are differences, if any, based solely on the stiffness, the weight, and the cellular structure of these different pieces. And in today's part one of this video, we are going to consider cedar, and then in part two of this video, we'll hear what spruce sounds like compared to cedar. So let's take a good listen to this cedar board. And if your hearing is very good and you're perceptive, you would have heard many different pitches. Probably not exactly what you expected, but boards like soundboards in a final guitar actually resonate in many different pitches. And the pitches that you maybe heard the most are maybe the lowest pitch and up to maybe the second lowest and maybe the third lowest. And it's very hard to discern in your brain, at least in my brain. I can only hear maybe the first three. So we can use a computer algorithm, and the one that I use is called Visual Analyzer, to actually analyze all the pitches that we're hearing. Now, you don't necessarily need to use such a computer algorithm in your selection process, but I just want to use it as an objective tool to illustrate what we're actually hearing. Here's the spectrum, and on the x-axis is the frequency in hertz, which means the number of times that the board is vibrating per second. But you can also think of frequency in terms of pitch, so that at low frequency you have low pitch, and at high frequency you have high pitch. And on the y-axis, we have the relative strength of those pitches, so that each peak that we see corresponds to the distinct pitches that we hear when we tap the board. So these peaks, also known as resonances, correspond to the sound output that our ears or the microphone picks up when we excited the board. It's a complex spectrum with a lot of peaks. In fact, a lot of peaks is what you want if you are a soundboard, because each peak represents the potential of the board to support and amplify a pitch that you play. Now, in my ear, I mainly pick up a particular pitch, and I'm just going to play it for you now. Here's the original tap that you heard, but I'm going to tap in a different place right now to accentuate this third peak. It's one of the higher pitches, and that corresponds to this peak right here. Maybe you can hear it. I'll do it again. Just a comment about using tap tones to judge the suitability of boards in this pretty raw state. It can be deceptive because the tap tones that we hear, as we will see, are really determined by the dimensions and the weight of different boards. So if you have different dimensions and you're comparing one board to another in terms of the tones that you hear, they're going to be different. And as we saw in this previous example, my ears were very attuned to this third peak, and a board with a different dimension won't necessarily have that frequency, but it could have other frequencies that are pretty lively, but maybe my ear just doesn't pick it up as well as that particular frequency. So as we'll see, using something like density, which is independent of the actual dimensions, could be a better measure. But at this raw state, it could be very useful to use in addition to just hearing the general liveliness of tap tones in a particular board. Well, like I mentioned, each one of these peaks can be thought of as the potential to resonate if you play a particular note when you play the guitar. So for comparison, here's what a completed guitar spectrum looks like, and it's filled with a lot of peaks, and that's exactly what you want. A good analogy is to think of each resonant peak as one gear in a large collection of gears in the soundboard engine, and so if you're missing a gear, the engine will run at very low efficiency at that particular range of pitch. Now this is where it starts to get interesting when we compare different boards from different soundboard sets. So let me play for you that first board that we just heard. And now let me play for you an equivalently sized piece of cedar from a different set. Let me just go back quickly to the first set. Quite a difference, right? And one is definitely higher pitched. The first sample is definitely higher pitched than the second sample. And what's different about these two pieces is that the second sample is a much lower density than the first one. So let's talk a little bit about what is density. Density is the weight of something for a given volume. For example, you know that a cup of sugar is heavier than a cup of flour because it's more dense. And mathematically, density is weight divided by the volume. And I'm going to show you how to calculate density for a soundboard. And what you need for it is a ruler, a caliper, and a scale. And feel free to pause the video so that you can do the calculation on your own. Now that you know how to calculate density, now let's take a look at how these two samples with different densities relate to one another in the spectra. So here is the spectrum of the first soundboard that you've already seen, and it turns out that it has a density of 0.38 grams per cubic centimeter. And for simplicity going forward, let's just consider the lowest frequency end of the spectrum. And let me blow it up for you. So here's what you saw in that yellow box, and it shows you essentially two major peaks, one at 82 hertz and one at 173 hertz. Now let's bring in the second sample, which has a density, a lower density at 0.3 grams per cubic centimeter. And you can see that the peaks of this fundamental frequency at around 70 to 80 hertz has shifted in the upper sample. And it shifted about 10 hertz, which is significant. And that's exactly what we heard in these sound samples. Let me play the sound samples for you again. First, the bottom sample at 0.38 grams per cubic centimeter. And compare that to the lighter sample at 0.30. Right? And so if we built soundboards with these different materials and we left the thicknesses exactly the same, that would have ramifications on the sound for sure. And one wouldn't necessarily be better than the other, but I can say that the one with the lower density soundboard would have a more bass-oriented sound, whereas the one with the denser soundboard would have them slightly shifted to the treble orientation in that sample. The reason why these pitches change is because density is highly correlated with flexibility. And so in the upper panel, the less dense sample is more flexible. And in the lower panel, that soundboard is more dense, and therefore it's stiffer. All right, so what's the relationship that's going on here? Well, it turns out that the pitches that we hear are related to stiffness. So if you have higher stiffness, you get higher pitch, and that's what we heard. You have lower stiffness, you have lower pitch. Okay, so we could observe that. Now, truth in advertising here, it's really that pitch is correlated to stiffness directly and inversely related to weight. So mathematically, we could say that pitch is correlated to stiffness divided by weight. For most things that we do in lutherie, like adding braces or carving away braces or thinning a soundboard, most of the time the stiffness will change much faster than the weight will change. And so for most approximations, we can simply factor out weight and say that the pitch usually is related to just the stiffness and kind of disregard the weight. But there are exceptions to this, of course. Consider when you add a brace, which adds stiffness, but it also adds a huge amount of weight. And so that could be a factor in determining pitch. Now, this is just for pitch, but of course weight will have severe consequences on volume and sustain, so just keep that in mind. That's a lot of physical theory, so let's get back to guitars and think about how this has implications on the sound and the consistency of guitars. Let me tell you about the range of densities that I prefer when I start projects, and the criteria are part of the design of the guitars. Here I show the densities that I'm typically interested in, ranging from 0.34 to 0.42 grams per cubic centimeter. If I'm building classical guitars with Western red cedar, the sweet spot for me has historically been between 0.34 and 0.38. And if I'm building with any kind of spruce, it will be between 0.36 and 0.40. And in general, spruce densities for a variety of spruce species will be higher because they're typically more dense than cedar, so my starting points are a little offset by the natural abundance of the materials available. Now here's where the design part comes in. If I build a solid top guitar, I'll go for the upper half of those density ranges because with a solid top I'm able to comfortably thin to an appropriate thickness to get the right flexibility that I need and still have enough plate thickness that it's not too thin and it's still easy to handle. However, if I'm building double tops where by design lightness is everything for the response and power, I go with densities in the lower half of those ranges. The ultra-thin soundboard veneers need to be light and really flexible in order to give the composite sandwich enough mobility. In a double top, I already have a middle core, so if my veneers are too stiff, I've nullified the design. And then finally on the far right, if I'm building a steel string, I'll go for even denser because the extra tension of the steel strings requires a stiffer structure. And just a comment here, in general I think some tone wood producers overemphasize how great it is that their wood is the stiffest wood available. Remember that to pump air and have power we need mobility and flexibility. Granted we need to resist a structural implosion, but Going too stiff can leave you with an inefficient guitar that's also too bright and lacks richness. By now, you've been introduced to a lot of concepts, and you've done a great job hanging in there with me. So let's wrap it all together and look at the bigger picture. Imagine if you had a stack of cedar with random boards that had densities all over the map, and then you built guitars with them using a robot to cut everything at the same shape and thickness. That's exactly what happens in high production factories. How do you think 100 guitars coming off the production line would sound? Definitely the resonant peaks would be all over the place, and they'd probably all sound different unless the peaks happened to line up by chance. And furthermore, some would sound better than others. I think having fun thinking about this, I think that it might turn out to look something like this bell curve that I show you in this graph. And subjectively, down here on the x-axis, I have sound quality, whatever that means, however you want to judge it. Let's just say that, a good sounding, excellent sounding guitar would be over here on the right, and a poor sounding one would be over here on the left. And the y-axis is the number of guitars that would fall in any of these categories. All right, so this is for a random density, same thickness guitar. I think that the shape of this curve would be kind of like a bell curve. You have a lot in the middle that have, kind of average sound. And just by luck, with the right combinations of densities of many different parts, not just the soundboard, but also like the bridge would have a high effect on the characteristic of the sound. By luck, a small number would end up in this excellent range, and a small number would also end up in this poor range, and I think some would end up kind of in the middle, just by randomness. All right. So now imagine if instead of random density, we could measure the density like we talked about, and then we made the soundboards at the same thickness, though. We would control the density, and now the resonances would probably be a little more uniform and predictable. And so I think that if we could control the density to something that we found is correlated with good sounding guitars, we should wind up with a curve over here in the green that shifts things more to the higher quality end. The bottom line is that selecting based on density already allows me to shape the sound even before I shape the wood. It's a great surrogate for knowing the inherent stiffness of a piece of soundboard material. The implications are that I can manage the consistency of sound from one guitar to another, or control the direction of sound even before I start cutting. Now, in later videos, we're going to discuss how to further refine and adjust and compensate so that we can get the curve over here, such as by thinning the top and carving the braces to distribute flexibility, and that can help push this curve even farther to this excellent range. That's plenty to think about in one video, so let's stop here and continue in part 2. And when we meet again, we'll talk about how spruce relates to cedar, both in material properties and sound. And then we'll talk a little bit about how thinning a soundboard can change the flexibility and the resonant properties. So thanks for your patience through this video, and I'll see you on the next part.